Hello ladies and gentlemen, this is Ms. Skokin. We're in section 8-3, solving right triangles. Our objective is use trigonometric ratios to find angle measures in right triangles and to solve real-world problems. And vocabulary, inverse trigonometric function. We've got 5 questions in our warm-up, and questions 1, 2, and 3 use the triangle ABC shown. So I'm going to ask you to pause the video and turn it back on when you're ready to check your answers. Good luck with these questions. The skills on these warm-up questions were a combination of some previous lessons that we've had, so hopefully you didn't have any trouble with those. I know the distance formula is a little bit tedious, but it's also not too hard, so it's a great way to refresh your memory on that. Anyhow, let's move on. We can use the trigonometric ratios and the Pythagorean triangle right angle relationships that we've learned to determine both side lengths, like we've been doing, and angles, which is something different that we haven't done yet. So let's take a look at example 1 on the next page to get started. In example 1, you can see that we have a right triangle, we have all 3 side lengths, and we have the 2 acute angles labeled 1 and 2. The question reads, use the trigonometric ratio cosine of angle A equals 24 over 25 to determine which angle of the triangle, angle 1 or angle 2, is angle A. We're going to try out both angles. So we're going to start out with the cosine of angle 1, defined as adjacent over hypotenuse. And if we're at angle 1, the adjacent measures 1.4 feet over the hypotenuse, which measures 5 feet. And that gives us 0.28. If we're at angle 2, then the cosine is still defined as adjacent over hypotenuse, but this time the adjacent measures 4.8, hypotenuse still measures 5. This ratio of the side lengths gives us 0.96. Now, the test value that we have, cosine of angle A, is equal to 24 over 25, which when we divide that out gives us 0.96. So we know, there it is, that the angle that is angle A is angle 2. So angle 2 is angle A. The point of this is just for us to remember that the cosine of an angle depends on which angle you're looking at. There's a now you try for you to work on, so pause the video while you're working on this one, turn the video back on when you're ready to check your answer, and figure out which one of the angles, 1 or 2, is angle A. See you back in a minute. After looking at the ratios of the adjacent over the hypotenuses, I'm sure you were able to determine that angle 1 was angle A on the now you try question. If we have the value of the sine, cosine, or tangent of an angle measure, then we can use the inverse trigonometric function to find the measure of that angle. For instance, if we know that the sine of angle A is equal to 1/2 and we want to find the measure of angle A, we might remember that we learned about special right triangles where the sine of the 30-degree angle of a right triangle is 1/2. And we remember that all 30, 60, 90 triangles are similar to one another, so that means that the measure of angle A must be 30 degrees. This is one way to look at this type of a question, but honestly, we can't remember every single sine ratio of every single angle. So what we're going to be doing is using our calculator, sometimes our memories, but mostly our calculator to help us out with this. Just a commentary about how we read something. We're going to be using these symbols, the inverse trigonometric functions. So inverse sine, inverse cosine, and inverse tangent. And the notation that we're going to be using is that sin for sine, or cos for cosine, or tan for tangent, with what looks like an exponent of -1. It's not actually an exponent. It is specific notation that we use to indicate an inverse function. So when we see that, we're going to read inverse sine of x. In example 2, we're going to use our calculators to find the angle measures to the nearest degree. And since each of our calculators is slightly different, I want you to write down the calculator steps for your calculator. I'll write down the calculator steps for my calculator to find the inverse cosine of 0.87. So the steps on my calculator is the second key, the cosine key, the number 0.87, and then the enter or the equals sign. And I get 29.5413605. But the instructions say to find the angle measured to the nearest degree. Properly rounded, the answer is 30 degrees. For question B, second key, sine key, 0.85 equals, and I get 58.211 and a few more decimals, properly rounded, 58 degrees. And for the inverse tangent of 0.71, again, use the second key, this time the tangent key, 0.71 equals, and I end up with a final answer of 35 degrees. So hopefully you now know the calculator steps for your calculator to do this correctly. If you have some questions, definitely bring your calculator class and we'll take a look at it together. We do something called solving a triangle, and what that means is we need to find every angle measurement and every side length of the triangle. When we solve a right triangle, we have a little bit of a head start because we already have one of the angles, the 90-degree angle. So we're going to be using trigonometric ratios and Pythagorean triangle relationships to find all of the sides and all of the angles of the triangle, of whatever triangle is in our problem. In example 3, we're starting out with the triangle in the diagram, and of course we have a few different ways that we can do this, and because of rounding we might end up with slightly different answers depending on how we get started on this. So I'm going to show you the different methods that we can use. For example 3, our instructions say find the unknown measures, round the side lengths to the nearest hundredth, and round angle measures to the nearest degree. Let's start out by labeling our triangle. Hypotenuse is the hypotenuse, and of course that's the side that's opposite the 90 degree. That side should be called lowercase s. The side that is opposite angle R should be called lowercase r, and opposite side T, or I'm sorry, opposite angle T, we have side T. So let's start out with method number 1 using the Pythagorean theorem to find the missing side length R. We start out with r squared plus t squared equals s squared, and then we substitute in our values. 5.7 squared is 32.49, and of course 5 squared is 25. The difference is 7.49, and when we take the square root of both sides, we end up to the 2 decimal places, 2.74. Now we have all 3 side lengths, but only one angle, so we need the other 2 angles. And what we're going to do is we're going to use our trigonometric ratios and our inverse trigonometric ratios to find one of the missing acute angles. So let's use the sine, and we'll use the sine of angle T. Sine of angle T is opposite over hypotenuse, and when we're at angle T, the opposite side is 5. The hypotenuse is 5.7, so it's going to be 5 over 5.7. I'm going to rewrite this so we have enough space to show using the inverse sign. Sine of t is equal to 5 over 5.7. Be very careful with the way you write this, because now what we're going to do is we're going to take the inverse sign of both sides. That means we're going to undo what was done to t. On that left-hand side, that means that we're going to end up, the way that the sine and the inverse sign cancel out, we're going to end up with the measure of angle t. On the right-hand side, we're going to be putting in our calculator the inverse, the second key, or the shift key to get the inverse trigonometric function, inverse sine, 5 divided by 5.7. which gives us 61 degrees, rounded to the nearest degree. Now we've got all 3 side lengths and 2 angles, so we can find the third angle very easily And the measure of angle R is equal to 90 minus 61, because we know the two acute angles of a right triangle are complementary, meaning they add up to 90. So we're going to end up with 29 degrees for the measure of angle R. Now we have solved the right triangle. Our final and complete answer is all of the angle measurements and all of the side lengths. Method number 2, we can start with the trigonometric ratios and not use the Pythagorean theorem. We can start with the cosine of angle R, which is defined as the adjacent over the hypotenuse. And just as we did a few minutes ago, we need to give ourselves a little bit of room to use the inverse function. So the cosine of angle R is equal to 5 over 5.7. Then we take the inverse cosine of both sides. On the left-hand side, we end up with the measure of angle R, and on the right-hand side, we're going to be in our calculator, inverse cosine of 5 over 5.7, giving us a measure of 29 degrees. To find that third angle, again, we can say that the measure of angle T is equal to 90 minus the measure of angle R, which is 29 degrees, giving us measure of angle T of 61 degrees. Now we've got all three angle measurements, and it's time to find the missing side length. Let's use the sine of angle R, which is defined as the opposite over the hypotenuse. Now, let's rewrite that, plugging in what we know. Sine of 29 degrees is equal to R, our missing value, our missing side length, divided by the length of the hypotenuse, 5.7. To solve for R, we're going to multiply both sides by 5.7, and the rest is calculator work. We find the length of R as rounded to the 2 decimal places, or the 100th place, as 2.76. As before, our final answer is all of the side lengths and all of the angles all put together. And both methods are good. It's not that one is better than the other. Some people favor one, some people favor the other. All of these are right triangle methods, and either way, you do need to use your inverse trigonometric functions. So let's take a look at the Now You Try on the next page so you can get a little bit of practice. Find the unknown measures in triangle ABC. Round the side lengths to the nearest hundredth and round angle measures to the nearest degree. Remember to label all of your work and to keep it organized so it's nice and neat. When you're done with everything, remember to put all of your 6 answers, the 3 side lengths and the 3 angle measures, in a nice, neat, organized answer box. See you back in a few minutes. Depending on what method you used and exactly where and when you rounded, you might have slightly different answers. But as long as it's close and you can follow the logic, if you're off slightly from the answers that I got, that's not a big deal, not a problem. All right. So you got some practice doing that. Now let's take a look at an application of the distance formula on the next page. In the old days, we used to call this type of geometry plane geometry because it was all done on a coordinate plane. And that's example number 4 is basically a throwback to that. What we have is the coordinates of triangle PQR. So we're going to graph triangle PQR so we can get an idea of what's going on, and then we're going to find the side lengths to the nearest hundredth and then the angle measures to the nearest degree. Let's start by graphing the triangle. Luckily, we've got a beautiful right triangle here, so we can calculate the horizontal and vertical lengths of the legs just by counting boxes. From P to Q, we have 5 units. Remember that this is also called side R. From P to R, we have 7 units, and this is also called side Q. Now, we have the distance from R to Q, and for that, we need to use the distance formula. So once we have the distance formula written down, we can plug in what we know. Remember that we're looking for the distance from Q to R. So let's plug the coordinates in and find the missing distance. So rounded to the nearest hundredth, our hypotenuse measures 8.60 units. We have all 3 side lengths now, and we need to find the angle measures that are missing. When we need to find a missing angle measurement and we have the side lengths, that means we're going to need an inverse trigonometric function. I'm going to vote for the inverse tangent so that we can use the two values that are the horizontal and vertical distances, and we don't have to use our rounded number. If we start at angle R, then little r is opposite and 7, the vertical, is adjacent. That means we're going to be using the inverse tangent. So if the tangent of r is equal to the opposite over the adjacent, which is 5/7, then when we take the inverse tangent of both sides, on the right-hand side, we're just going to have the measure of angle r, and on the left-hand side, we're going to have the measure of angle r, and on the right-hand side, we're going to do some calculator work to come up with 36 degrees when rounded to the nearest degree. Last of all, we need to find the measure of angle Q, and we know that the measure of angle Q is going to be 90 minus the measure of angle R, which is, we just found was 36, so the measure of angle Q is going to be 54 degrees. We've now got all three side lengths and all three angle measurements. And our final answer is shown all together in our answer box. You've guessed it, now there's a Now You Try to work on, and you can use the one that we just did as a model. Turn the video back on when you're ready to check your answers. You may want to start by graphing the triangle. See you back in a minute. These questions are not hard, but they do take a long time. There's a lot involved. So I know you're glad to be finished with that one. And obviously you wouldn't have many of these, maybe one on a test, because they do take a long time. All right, let's take a look at another application of the inverse trigonometric functions on the next page for example 5. Example 5 reads, a highway sign warns that a section of the road ahead has a 7% grade, also known as a gradient or slope or steepness. To the nearest degree, what angle does the road make with a horizontal line? Although we have a picture of the road sign, it's definitely going to be helpful to us to have a diagram. So let's draw a triangle to start with. We have a triangle. We can label it A, B, C. We know that this is a right angle at C, and we know that we're interested in the angle with the horizontal, so the angle with the ground that the road makes. So let's go ahead and label the names of our sides. This is our hypotenuse. Across from angle A is our opposite, and of course, this is our adjacent. Side names are A, B, and C. Now we're all set up for problem solving. All right, so they've given us information that the road is making a 7% grade with the horizontal. And this is something that we really haven't seen before. So this is a new way of looking at it. And one way that we can approach this strategically is to say that it's a 7% tangent. All right. So we could say that the tangent of angle A, which is opposite over adjacent, is 7%, or 7 out of 100. That doesn't mean that the adjacent is equal to 100 or that the opposite is equal to 7, but it means that the ratio between the opposite and the adjacent is 7%. So we can use that information, though, and our inverse tangent to find the measure of angle A, which is the angle that the road makes with the horizontal line. So if the tangent of angle A is 0.07, and we take the inverse tangent of both sides, then on the left-hand side, we're going to have the measure of angle A, which is what we're looking for. And on the right-hand side, we've got a little bit of calculator work to do, but we end up with 4 degrees. So a grade of 7% results in an angle of 4 degrees. It's kind of like two different ways of measuring the same thing. All right, you've got a Now You Try to work on, and it is very similar to this question. So I'm going to ask you to pause the video This is the last question before you get to start on your homework problem. So I'm going to ask you to pause the video, work on this one, and then turn the video back on to check your answers. Remember to start by writing down all the important information in the question and by making a diagram for yourself. See you back in a minute. If you followed the model of the question that we did together, then this Lombard Street question should have been pretty easy for you, and you were able to find a 40-degree angle with the horizontal. That is it for this section, and I will see you back as we continue on in Chapter 8, all about right triangles.